Greeting esteemed audience. My name is Lubash Abir, and I am a PhD student of architecture at Guelma University in Algeria. I am privileged to participate in this conference, and I would like to present my research findings on heat waves in the city, evaluating and mapping vulnerability case study Algeria Guelma. I will give you a quick outline of my content with a table of contents. Introduction, literature review, methodology, results and discussion, and finally the conclusion. Let's start first with the introduction. Heat waves present significant challenges to urban environments worldwide, threatening the health and well-being of city residents. The increase in frequency, intensity, and duration of heat waves, compounded by urban heat islands, have made cities exceptionally vulnerable to these extreme weather events. Urban areas experience heightened impacts from heat waves due to factors such as rapid urbanization, widespread use of man-made materials, and high population density. Understanding the spatio-temporal patterns and underlying drivers of heat waves is crucial for developing effective mitigation and adaptation strategies. However, gaps persist in our comprehension of the physical mechanisms and interactions contributing to heat wave occurrences, hindering accurate forecasts and regional projections. Addressing these challenges require interdisciplinary research, sustained observational networks, and advanced modeling techniques. The impacts of heat waves on cities are multifaceted, encompassing direct effects on public health, significant economic and environmental repercussions. Numerous research endeavors are underway to assess cities' vulnerability to heat waves, employing diverse methods and approaches, including empirical methodologies and sophisticated computer models, along with comprehensive literature reviews to inform research methodologies. This study specifically focuses on assessing the vulnerability of the city of Guelma to heat waves, integrating a thorough literature review into its methodology to develop adapted solutions for its unique context. Second, literature review of different heat wave assessment methods. Before the 2000s, general meteorological observations and temperature surveys involving direct collection of meteorological data in the field using measuring instruments. Between 2000 and 2020, the use of satellite data to examine various aspects of urban heat islands such as surface temperature, land cover, etc. Numerical simulations such as computational fluid dynamics models to conduct atmospheric simulations and model heat in urban areas. The advent of high-resolution remote sensing, which allowed for fine analysis of urban temperatures from satellite sensors. Integration of spatial analysis and GIS tools to map heat and assess its impacts on the urban environment. From the 2020s onwards, the increase in application of machine learning techniques such as prediction algorithms to enhance the prediction of urban heat waves. These algorithms can be trained using historical data on weather conditions, urban characteristics, and other relevant variables. Over time, researchers have adopted multiple approaches, but GIS and remote sensing continue to offer significant advantages. They allow for the analysis of variables such as population, land cover use, local climate zones, and building characteristics, which influence vulnerability to heat risks. Briefly, based on the study of various articles assessing urban vulnerability to heat waves, it can be observed that the choice of approaches varies depending on the intervention scale, tools, and available data. However, these methods can be grouped into three main categories as the following: air measurements by sensors, measurements of land surface temperatures from satellite images, and models. Material and methods. Upon a thorough review of numerous articles, we have selected 15 articles that present the primary approaches utilized to analyze and map heat waves in urban areas. Subsequently, a comprehensive depiction of the study area Guelma will be presented. After evaluating various approaches, remote sensing and geographic information systems were selected to be applied to Guelma. Remote sensing and GIS approach for mapping vulnerability to heat waves in Guelma. Our study uses remote sensing to classify land use and estimate land surface temperature. The land classification uses Landsat images from the 1990s to 2020. Four main classes are identified: urban areas, forests, agricultural land, and bare land, to estimate the LST. The thermal bands of the Landsat images are used, as well as an algorithm based on the NDVI vegetation index to calculate the emissivity of the Earth's surface. The LST is then estimated from these data. By combining this information, the study aims to better understand and map the vulnerability of urban areas to heat waves. Presentation of the case study, Guelma, an Algerian city. Our case study, intercommunal grouping of Guelma, is located in the center of the province of Guelma, in the northeast of Algeria. This region covers a total area of 282.11 square kilometers and has a semi-arid climate with cool winters, an average annual temperature of 21.5 degrees, and an average annual rainfall of 150.3 millimeters. Results and discussion. Mapping and interpretation of Guelma's vulnerability to heat waves. The study's findings highlighted significant urban expansion in the intercommunal group of Guelma between 1990 and 2020, leading to notable changes in land cover and biophysical characteristics. This increase in urbanization has also associated with an escalation in vulnerability to heat waves in the region. Land surface temperatures have risen, particularly in urban areas, bare lands, and vegetative devoid agricultural zones, indicating an increasing risk of urban heat, as we see in the following figures. A significant correlation was observed between land cover classes and LST, underscoring the impact of land use changes on urban heat distribution. Urban biophysical indices such as NDBI showed a trend of increasing over time, while vegetation biophysical indices such as NDVI decreased. These changes signify a transformation in the urban landscape that may exacerbate vulnerability to heat waves by reducing green spaces and increasing impermeable surfaces. Analysis of the relationship between urban biophysics and LST revealed a positive correlation, indicating that the increase in urban biophysical indices is associated with an increase in LST, while a negative correlation was observed between vegetation biophysical indices and LST. These results suggest that reducing vegetation and increasing impermeable surfaces may contribute to increased vulnerability to heat waves by promoting the formation of urban heat islands. Conclusion. Urban expansion in Guelma has not altered the urban landscape and biophysical characteristics, but has also heightened vulnerability to heat waves. Understanding these complex interactions between urbanization, landscape features, and vulnerability to heat waves is essential for developing effective and resilient adaptation strategies to cope with the impacts of climate change in urban areas. I would like to express my sincere gratitude for your attention.